without any further ado, I'll get into some of these concepts that we need to understand. Follow me through, and what I'll do is I'll back all this up with a fairly detailed post on the forum to just cover some of the things. As I said, I'll do two videos. One will be theoretical, and then the second video I hope to actually show you some practical setup with the blade angle on the helicopter itself. But as for definitions, first definition we need to understand is aerofoil. What is an aerofoil? Aerofoil is the actual shape of the blade itself. Okay, so that cross section of the rotor blade, whether it's a wing, whether it's a rotor blade, it's still an aerofoil. Okay, that's your basic aerofoil shape. The second phrase, the relative airflow, is simply the direction of the wind coming in and meeting that aerofoil. Okay, is it coming in from that angle, is it coming in from that angle, or is it coming in from that angle? Because the relationship between this aerofoil and the relative airflow is really what aerodynamics is all about. The third term, the chord line. The chord line is a line drawn from the very beginning of the aerofoil to the trailing edge of the aerofoil, and I've got a little diagram here that might show that a little more clearly. Okay, you can see there's a line there. This line running straight down here goes from the forward edge of the aerofoil to the trailing edge of the aerofoil. It's a straight line joining those 2 points. That's called the chord line. Chord line is important because that's where we take all our measurements of blade angle. Leads us on to the fourth point, which is angle of attack. The angle of attack is the angle between the chord line and the relative airflow, which is coming in here. So the angle of attack is the angle in which the chord line meets the relative airflow. This is virtually zero angle of attack, 0 degrees. That's probably about 10 degrees angle of attack. That's 45 degrees angle of attack. Okay, and you can also have negative angles of attack. So that might be about negative or minus 10 degrees, and that's minus 45 degrees. Okay, now to understand aerodynamics we could talk all day with formulas and mathematics, but it's really not that difficult. From a pilot's perspective, you don't need to be thinking about all that sort of stuff when you're flying an aeroplane. All you need to do is have a conceptual understanding of what is happening. And if we think about the total reaction on the wing, which is point number 5, is simply the air pressure being exerted on this aerofoil at any given time during flight. And that air pressure is a result of a number of different things. One is the actual speed. The faster it's going, the faster that aerofoil is moving through the air, whether it's a wing on an aeroplane moving forward or whether it's the rotor spinning around and around. The higher the rotor RPM, the faster the blade's moving. That is all going to determine the total reaction. Another factor that determines the total reaction is this angle of attack, because the total reaction on the wing actually moves as you change this angle of attack. And where this force is coming from is the fact that air meeting this aerofoil has mass. Okay, it actually weighs something, and as we increase the angle of attack, we're deflecting that air, in this case downwards. So we're forcing an object with mass, which is the air, downwards, and that requires energy. Now the opposing force to that is the force exerted on the aerofoil itself, which is the total reaction, and it's always going to be at 90 degrees to the angle of attack. Let's see if I can demonstrate it better with this diagram here. This is showing a couple of different forces, and this N symbol here is the total reaction. So it's basically at 90 degrees to the chord line of the wing at all times. Okay, so as we increase this angle of attack, this total reaction tilts backwards. So that's what the total reaction is. The total reaction is then divided up, for explanation purposes, into two different forces. One is the lift and the other one is the drag. And the lift is always resolved to be at 90 degrees to this relative airflow. So the airflow is coming in and the lift is resolved at 90 degrees towards that. the drag is resolved parallel with the relative airflow. So on our aerofoil, on our rotor blade, we now have two forces that we need to consider. One is the lift and one is the drag. Let's talk about lift for a minute. Lift occurs because the airflow is being deflected downwards. The opposite reaction to that is to create this total reaction, and we're resolving a vertical component that we call lift. The greater the angle of attack, the more lift we're going to get. Another factor affects the amount of lift, and that is the forward speed of the wing. Because the faster we're moving, the more air we're deflecting in any given period of time, so we're generating more lift. So two things affect the lift of the wing: speed and angle of attack. Okay, speed in our helicopter is determined by the rotor RPM that we establish, and angle of attack is established by our collective servos. They move the angle of attack as we move our control stick on the transmitter. Now those two figures work together. We've got lift and we've got drag occurring at all times. Now the greater the angle of attack, the greater the amount of lift we get, but the greater amount of drag we get at the same time. Now what happens there is that we end up with a ratio of lift to drag. Now this is a little bit of a complex curve when you first look at it, but let me just stick it up here for you. It might make sense. Can you see all that? Yeah, not quite. Okay, let me just explain what we're looking at here. This blue curve represents the amount of lift being produced by the wing at different angles of attack. If you can see angle of attack down the bottom, you've got 0 degrees angle of attack, 2 degrees, 4 degrees, 6 degrees, and so forth. So we've got our angle of attack increasing and our lift is increasing. The orange curve here represents the drag being generated. So as we increase the angle of attack, the drag on the wing is increasing at the same time. Now the term lift drag ratio, which is item number 8 on the list, is the lift divided by the drag. So it's almost like a ratio of how efficiently that wing or aerofoil is developing lift. It's always developing lift, but if you're getting a large drag penalty at the same time, then you have a fairly poor lift to drag ratio. This black curve represents the lift to drag ratio. Where it's at a peak is where you're developing the best or most efficient lift, because you're developing lift at minimum drag penalty. And ideally, if we can establish our helicopter to hover with an optimum lift drag ratio on the aerofoil blade, it means better battery endurance. That's really what it boils down to. We can hover at a higher angle of attack with a lower rotor RPM, and that's going to work fine, except you're going to have a lot more drag, which means you're draining power out of your battery faster. If you are flying below the optimum lift drag ratio, it means you're probably driving that rotor RPM way too fast with not enough angle of attack, and again, you're not getting maximum efficiency out of the system. And the final thing I need to discuss here is the stall angle, the critical angle. It's not really something that we encounter with our helicopters, but it is important to understand that once you move beyond a certain angle, you're not going to get increased lift anymore. You're actually going to get reduced lift. And what happens there is the airflow, as it approaches the aerofoil, it moves over the top of the surface and underneath. And when that angle of attack becomes excessive over the top of the surface, the airflow can't follow the curvature of the aerofoil, and it breaks away and it becomes turbulent. And that's called the stalling angle. And you can see in this curve here the blue point where it peaks and then drops off, and it's peaking there at about 9 degrees. Okay, it's probably a little bit low, but 9 degrees. Any increase in angle of attack greater than 9 degrees in this case is going to cause a reduction in lift. Now, more realistically, it's probably up around 12 or 13 degrees in our helicopter blades because of the design of these aerofoils. So you're not really going to experience any rotor stall unless you crank up or increase your blade angle of attack to more than 12 degrees, which is pretty extreme. I don't think either any of us is going to need that much. I have mine set to a maximum of about plus 10 degrees, minus 10 degrees. So we're not really going to encounter any of this stall situation. Okay, so just to recap, what we've looked at is the aerofoil, which is the shape of the cross section of the rotor blade. The relative airflow is the wind direction coming into that aerofoil. The chord line is a definition of the line between the leading edge of the wing and the trailing edge of the wing, a straight line. The angle of attack is the angle at which the chord line meets the relative airflow. The total reaction is the overall reaction caused by that meeting of the air in the aerofoil. The lift is the vertical component resolved relative to the relative airflow. The drag is the parallel component to the relative airflow. The lift-drag ratio is a term to cover the efficiency of how well it's producing lift. And remember, we want to try and get our helicopter hovering at the optimum lift-drag ratio so that we can conserve our batteries. And stalling angle is when we go too far with this angle of attack and the airflow breaks away. I just realised my video is coming up to about 12 minutes. That took longer than I thought, so I'll have to break this up into 3 separate videos. So I'll stop this video now and I'll start on the second one, which is a small computer program that will explain this a lot more clearly.